All right, let's get started. First of all, welcome to our build session. So I hope you all had a wonderful build journey here. So my name is Nathan Yan. I'm currently working on AI framework in Azure and working on ONNX and ONNX Runtime.
Hi, I'm Manas Goswami. I work with Nathan. I'm a PM in the AI frameworks team, and I work on the ONNX Runtime.
I'm Rajiv Nalawadi. I'm the architect at Intel, working on AI initiatives.
All right, thank you. So first of all, I want to know how many of you knows about ONNX? Great, awesome. So today we are very happy to talk about ONNX in enterprise and how Microsoft scales machine learning across the world and across the devices. So hopefully by the end of this session, you could understand the benefits of ONNX and ONNX Runtime. And you are able to leverage ONNX with our hardware accelerators, such as Intel hardware and NVIDIA hardware. And also, you are able to use ONNX in the cloud through Azure Machine Learning to build your AI applications. So first of all, let's take a look at the machine learning scale within Microsoft we are dealing with. So let's look at those numbers. So in Office 365, we have over 180 million monthly active users. And those users are actively leveraging the AI features we build, such as the PowerPoint translator, which can translate in real time while you are speaking. And it's available in more than 60 languages. Very cool, right? And it leverages the state-of-the-art speech recognition, machine translation technologies. And in Bing and Cortana, we have tens of billions questions were asked. And we have to teach the machine to really read the content in the web to provide the precise answering. And moreover, across hundreds of millions of Windows devices, every day, our machine learning leverages trillions of signals to identify the emerging threat on those devices to protect our customer data and assets. As you can see, the scale of machine learning within Microsoft is really huge, and the impact is profound. More importantly, it's still rapidly growing. Almost every single team, every single product within Microsoft is trying to leverage machine learning to improve the product quality and delight our end users. From HoloLens to Xbox, from Windows to Office, from Skype to Bing Search. And we have seen great opportunity and great potential to leverage more and more machine learning technologies to improve our product quality. But at the same time, we are also facing critical challenges, especially when we try to deploy those machine learning models to production. So let's take a look at the challenges. So before that, I would like to ask a quick question. So how many machine learning frameworks do you think Microsoft is using? Anyone have rough numbers? Anyone? 4? 10? So actually, we have seen more than 6 machine learning frameworks has been used within Microsoft across different teams. And even with a single engineer team, we have seen different developers use different training frameworks. I think it's quite common, even with like outside of Microsoft, because we actually encourage our developers to choose whatever best tool they prefer to do the machine learning training to improve their daily productivity. But training a machine learning model is just a start rather than end. By end of the day, we want to deploy our machine learning models to production, right? So our customers can get values from it. Then let's take a look of what happens when we deploy the model to production. So basically, when you deploy machine learning model to production, you might have different deployment targets, such as you want to deploy to cloud, to the IoT devices, to the desktops, and against a variety of hardwares, such as CPU, GPU, FPGA, and etc. You might be able to manage if you only have one training framework, you only have one type of model. But given we have so many training frameworks and we have so many deployment targets, eventually the combination of those two become a matrix. And the matrix only grows when your training framework grows, when your deployment targets grows. Right? How do you manage that? It's not really scalable. It not only introduces great challenges about your production deployment and also the maintenance, but it also jeopardizes your application performance. Right? Think about that. You have one application, but you have to integrate 6 training frameworks and ship with your production model. And each of those frameworks might create their own thread pools and compete with the resources, and it slows down your application. How do we solve this? Before we talk about solution, we want to take a step back to say why this is happening in the first place, right? This is happening because we coupled the training and the production inference. That said, whatever tool, whatever framework you use for training, you have to use it for online inference. To really solve this, we have to decouple those two. And we have to introduce something in the middle, right? And to bridge the both sides, we don't have to couple them together. Now you might know the answer. So the solution is ONNX. ONNX represents Open Neural Net Exchange. It is open and interoperable. So it becomes our industry standard. Basically, whatever the training framework you use when you train a machine learning model, you can convert that model to ONNX. And then at the production deployment time, you can just deploy ONNX model instead of the original model. And you can choose whatever frameworks that supports ONNX for production inference. And within Microsoft, we build a cross-platform and high-performance runtime. We call it ONNX Runtime. And we're going to talk about it in the following sessions. In order to really make ONNX really successful, we need a strong community support. We need to build a strong ecosystem. Because it's becoming an industry standard. As we speak today, so we already have more than 20 partners in the ONNX ecosystem. So they all support ONNX, which means whatever framework from all these partners, you can convert the model from those frameworks to ONNX. And also they can also load the ONNX models for inference. So now, I guess you guys have some basic idea of what is ONNX and where it is coming from. Right? You understand the challenges we are trying to solve. But I know you might be still wondering, right? So it sounds all good, but whether ONNX is really mature enough, really ready for production usage, right? So you might be wondering whether Microsoft is really using ONNX and ONNX Runtime in your product. I think it's a fair point because any new industry standard takes time to mature. So I want to tell you the answer is definitely yes. That's why in the next few minutes, I want to walk you through a few real production usage of ONNX and ONNX Runtime to show you how ONNX and ONNX Runtime really bring business values to our customers, to Microsoft products. So before that, I want to quickly mention that to really make our developer experience better, we have make ONNX general available on hundreds of millions of Windows devices through Windows machine learning. To all the cloud developers through Azure machine learning. And to all the .NET community developers through machine learning.net. So for all those customers, you can easily access ONNX and ONNX Runtime. And in terms of the adoption within Microsoft, ONNX and ONNX Runtime has been widely adopted to the Microsoft products such as Bing, Bing Ads, Cognitive Service, Office 365, so on. So let's take a look at some real use cases. So the first use case I want to talk about is Office 365. As I mentioned earlier, Office has been heavily leveraged machine learning to improve the user experience. And here is just one simple example. Why I choose this as an example? It looks simple, right? Because I, as an English learner, as a non-native English speaker, I have found it very useful. And in fact, there are 1 billion, more than 1 billion English learners across the world. And even within the United States, there are more than 4.8 million English learner students. And the Office has built this grammar check to really provide a handy tool for those users to improve their daily life. So as you can see, hundreds of millions of users are using this feature every day in real time. So the performance of this model is really matters. And actually, our feature team in the past year has been actively seeking for solutions to bring down the cost and reduce the latency. Luckily, we have ONNX and ONNX Runtime. So another question. So how much faster do you think this model can run after switching to ONNX and ONNX Runtime? Anyone has a rough guess? Anyone? I like your answer. Pretty bold. I may let you down a little bit this time, but we will work harder. So we have seen 14.6 times when we deploy this model with ONNX and ONNX Runtime. Pretty amazing, right? This is way beyond our customers' expectation. And if you look at the right-hand side, that's the latency graph when we deploy ONNX and ONNX Runtime to production. As you can see, the latency drops dramatically and it becomes flat. This is the value we want to bring to our customers and to our products. So the next use case is actually one of my favorite. It's called OCR. This is available in the Azure Cognitive Services. It's basically a pre-trained model. So how many of you knows what OCR is? Great, thank you. So it basically extracts the text through an image, right? So for example, someone give you a note, handwritten note, right? You can take a picture and get the text. You don't have to type. And amazingly, it doesn't have to be in the right angle, right? Even you put the note upside down, our OCR cognitive service can recognize that. And not just like that. Our OCR cognitive service can even read the product labels. For example, you go to the like a supermarket, and you want to get all the nutrition of a product, right? You can just take a picture. And for those labels, it is not necessarily on a flat surface. It can be on a cylinder, right? It introduces the challenges. But our OCR model can easily read all the text for you. And even more, it can read the road signs, right? Think about if you train this model to a real-time text-to-speech model. You can quickly build an application, right, to help the blind people to guide them on the street. And if you hook up this model to a real-time translation, then you can quickly build a travel application, right, for those people that cannot speak that language, but they still can recognize the road signs, right, the labels on the street. How cool it is. Actually, the quality of the OCR cognitive service of Microsoft is pretty competitive in the market in terms of the quality. But we are actually lagging behind in terms of the latency and the performance. And with ONNX and ONNX Runtime, we are able to speed up this model by 3.5 times, which makes our cognitive service very competitive in both of the quality and the performance. So not just the Office and the cognitive service, our Bing search team has traditionally heavily leveraging the machine learning technologies to improve the search quality and to enable new scenarios. In the past few years, there's a new emerging scenario about a search. We call it a question and answering. That's actually triggered by personal assistant like Cortana and Alexa. Right? In Cortana and Alexa, people are expecting the direct answers about those open questions instead of giving you 10 blue links. Right? How do we do it? For this, we have to teach this machine to able to read the content, read all the web pages, and understand that from a semantic point of view, and then correlate it back to the user's intention. As you can imagine, those machine learning models are pretty expensive. And with ONNX and ONNX Runtime, we are able to speed up those models by 2.8 times, which really brings a great value to our product team. And not just those keyword search, Bing also have high quality multimedia search. And traditionally, for image search, if you think about that, in the past, right, we not really look at the content of the images. Instead, the search is actually using the user's keyword and correlate that to the surrounding text of the images in the web page. That's how the image search has done in the past. But as you can see, there are clear drawbacks of this approach. It's simple, but it introduces desets, right? Because sometimes the image just itself is not talking about the surrounding text. How do we solve this? So we have to train a machine learning model to really understand what's inside the image. What's the semantic meaning of that image? And with ONNX and ONNX Runtime, we are able to speed up this model by 1.8 times. So the last use case I would like to talk about is Bing Visual Search. It's getting more and more attention, especially in the mobile world. Because many times in the mobile, you don't want to search by keywords. You want to search by images, right? You walk on the street, you see some flowers you really like, but you don't know what it is. You want to find it out. So you take a picture and search the image, right? Then the Bing search can tell you what the flower is or what the dog is. Under the hood, we have been building this Bing Visual Search, and ONNX and ONNX Runtime is empowering those machine learning models. And because they are pretty expensive, we are leveraging the hardware accelerators like GPU. And with ONNX and ONNX Runtime, we can get up to 2 times performance improvement. And the performance improvement will vary depending on what kind of hardware you're using. As you can see, ONNX and ONNX Runtime has been adopted widely across many Microsoft products, and it brings real business value to our customers and to our Microsoft products. Right? Not only make our production deployment easier, right? Make it scalable and easy to maintain, but also provides significant performance improvement and cost saving. So we hope you could find ONNX and ONNX Runtime useful. You could leverage that to bring business value to your customers, to your application as well. So with that, I'm going to welcome Manish to the stage to talk about our hardware strategy and partnership.
Thank you, Nathan. So what I'm going to talk about is how we operationalize your AI application. We're using ONNX Runtime and what we are doing with our hardware ecosystem partners. But taking a step back, at Microsoft, we look at the edge as an extension of the cloud. By that, I mean that we are increasingly seeing that the compute needs to go near where the data is collected. And in that environment, we come upon very different set of hardware platforms, as well as hardware optimizations that are done to run computations that are critical for neural network or machine learning models. For us, the same consistency that we are driving for our internal workloads, we would like to drive that between the cloud and the edge for AI applications. And that we would do by way of ONNX as the common representation of your machine learning model. We view ONNX as a single interface which enables us to decouple your training and development, application development environment from how we may execute that compute workload across the cloud on a hybrid edge device, as well as all the way down to light edge devices where you may do very, very basic neural network computations. We would do all of that with the ONNX Runtime. The ONNX Runtime is an open source inference engine for ONNX models. It is available across a variety of platforms in Mac, Windows, as well as Linux. It runs on x64 as well as ARM-based architectures. And sorry about that. And additionally, the ONNX Runtime is part of the WinML engine that is available in Windows. The ONNX Runtime at a high level is a graph parser which parses the ONNX graph and does additional optimizations like fusing ops. Then it interfaces with underlying hardware libraries to enable you to take certain parts of the subgraph and execute it on that specific hardware that's available and where you have deployed your model. This allows us to fully optimize the execution of the model on that specific target hardware, whereas the ONNX model's representation remains consistent, and your application interface that you would use to initiate the inference session or load the model doesn't change across the platforms. In terms of the ecosystem, this is going to be a journey for us. We will continue to grow. But when we look at the different types of processors that are available or that are used. We look at CPUs, GPUs, and FPGAs being mainly cloud-based, but not entirely or exclusive to the cloud. And there we have a rich ecosystem of partners that we are working with to build the execution provider interface, which is used to run the ONNX model at that specific hardware platform. So we have our partners Intel, who's going to come and talk about the work that we have done together with them as it relates to the ONNX runtime optimization. And additionally, I would like to mention that we have been working with NVIDIA to work on the TensorRT and CUDA-based execution providers. And today we are disclosing here that there is an OpenVINO-based execution provider that's in private preview. So those of you partners who are interested to work with that, please talk to us or your counterparts or contacts at Intel. With that, Rajiv, I'd like to invite you on stage.
Thank you, Manash. So Intel has a wide array of hardware offerings spanning across CPU generations such as Atom, Core, Xeon, and FPGAs, vision processing units, GPUs, ASICs, as well as the low-powered components like GNA, which are integrated into our SoCs. So to support this wide array of hardware offerings, we are integrating 3 execution providers: MKLDNN, ngraph, and OpenVINO. And MKLDNN gives developers the flexibility to invoke individual kernels, whereas ngraph and OpenVINO provide like the best performance by doing graph fusion for all the AI workloads. So with OpenVINO and ONNX runtime merge that Manash just mentioned, we should be able to apply that to various verticals, such as manufacturing, retail, connected logistics, transportation, smart cities, robotics, and so on. And combine that with the readily available dev kits, which are out there in the market. The link is there in this presentation. You can order them anytime, readily available right now. So IEI is one such dev kit, and it could be applied to a manufacturing segment. And you can add additional accelerators as required, FPGA or VPUs. And also, like UpSquared is another dev kit which is available out there and could be applied for the retail segment. And that also allows additional accelerators to be added. And there is the neural compute stick as well, which could be plugged into any platform to accelerate the AI workloads. So with this combination of ONNX runtime, OpenVINO, and the dev kits, the customer should be able to take their proof of concept solutions to a market-ready solution in a very timely manner. So next, Microsoft and Intel collaborated on quantization to showcase quantization on a recently launched Cascade Lake processor. Basically, quantization here is a set of techniques you apply to convert your FP32 model to a lower precision data type. In this case, it is int8. So basically, you get like a lot of benefits. Theoretically, you should be able to get like 4x lower memory bandwidth, and then the reduction in the memory footprint of the model, and increased number of tops per watt as the compute increases with the lower precision. And we want to do all of these with a minimal loss of accuracy. So I'll go over some of the results that we have achieved, but a very quick background on what is quantization and how it's applicable to our Intel products. So on our previous generation processor called as Skylake, you could be able to execute int8 quantized models. So basically, you had a vector processing multiply add instruction at the byte level, and then a vector processing multiply add at the word level, and then a vector processing add at the dword level. So there were 3 instructions that were required on this older generation Skylake processor. But you could still execute both FP32 models as well as int8 models, even on our previous generation processors. On the recently launched Cascade Lake processor, there is an instruction set called as Vector Neural Network Instructions, or VNNI for short. And it's also referred to as DL Boost. So basically, it does a fusion of these 3 instructions to provide a single instruction now called VPDP BUSD. So with this single instruction, you could replace all those 3 individual instructions in the integer gem kernels to yield a better performance. So basically, you could start out with a vector processing instruction like VPDP BUSD and feed it like an unsigned 8-bit for input and activations, or a signed 8-bit, which is typically the case for weights in the convolution. So you have 8-bit convolution computes here, and it will generate a signed 32-bit output. So this should theoretically allow for 4x more compute and 4x 1/4 the memory requirement. So we'll see how we did essentially. So as an example of a ResNet 50 model, and here are the numbers essentially which are shown between Skylake FP32 model and a Cascade Lake Int8 VNNI model. Essentially, the configuration was kept the same. The Skylake had a similar configuration. For example, the number of cores, memory, as well as the frequency was limited and the same on both the Cascade Lake as well as the Skylake processor. We wanted to showcase the real benefit of VNNI here. So we kept the configuration the same. So here, in case of the raw numbers, you could be able to get like more throughput images per second if you were to use Cascade Lake and with all the generational improvements of the frequency and the cache and so on. But in this case, the data here is showing the same configuration of Skylake and Cascade Lake. And as you can see with ResNet, we were able to use ngraph, combination of our hardware processor capability along with our ngraph as an execution provider, which does the graph fusion. We were able to get like a good scaling in terms of performance, going in from various batch sizes of 1 all the way to 32. Batch size of 1 is very critical because there is a REST API, for example, being computed on the cloud. So even there, we got a better performance, like around 3x. And if you look at even the batch size compute, it was 3.4x. And the memory model itself, the size was about 1/3 the size. And with a very little loss of accuracy, essentially 0.41 for top 1 and 0.21 loss for a top 5. So we were able to kind of meet all the motivational benefits of what quantization provides. Not just with ResNet 50, we were able to showcase the same kind of results with Inception V3 model as well. So here you can see again the scaling with respect to batch size of 1 all the way to batch size of 32. We went from 2.28x all the way to 3.67. And 3.67 gets us very close to that theoretical limit that we talked about of what we should be able to achieve going in from FP32 to Int8. And again, a very little loss of accuracy, 0.30 for top 1 and a 0.08 loss for top 5. So we are very excited about these results, and the work continues on the quantization side from Intel and Microsoft.
So thanks. Thanks, Rajiv. Okay, now I'm going to go show you some demos, right? But those were very impressive numbers. When you look at building an AI application with ONNX models, there are a number of ways you get to an ONNX model. There is an ONNX model zoo, where you have open source models that have been published. The custom vision services from Microsoft also allows you to export to ONNX. You can bring your own ONNX model, and then you can use Azure machine learning experimentation to generate your ONNX model. The ONNX model zoo is in GitHub /ONNX models. You can download them and use them in your own application as needed. The custom vision interface allows you to upload images that are targeting your scenario. You can build a model based on the training service there, and then there is an option for you to export that model to ONNX. This model can then be ingested into your AI application or into your AML model registry, which I'm going to show you in a bit. In addition, when you have your own model and you've built it in your own training framework, there are a variety of converters that are available. And these converters will allow you to generate the ONNX graph from your development platform, and then you can use the ONNX runtime to run your inference sessions within your application. So here are a few code snippets of how you could be converting the model. It's very consistent. We aim to provide consistency so that your code or the work that you'd have to do to export your models to ONNX is very, very similar across all the training frameworks. And all of these are available and open source converters that you should be able to access through GitHub. In the ONNX runtime, once you have the model in ONNX, you would essentially have to do two steps. In addition to all the pre-processing and post-processing that your application requires, you would load the model into the ONNX runtime. This is the process at which the ONNX runtime starts parsing the graph and tries to identify available optimizations. Parallelly, the ONNX runtime also will query the underlying hardware to identify what kind of operations the hardware libraries will support, and then makes a decision of partitioning the subgraph to allocate specific ops to that hardware execution engine. So that's the integration work we do across our hardware partners with Intel, NVIDIA, and others in the pipeline that we have not disclosed. So as you can see, in the code for Python and C# are very similar. So what, again, we are driving towards is consistency so that your application code does not need to change based on the environment that you're using it in. The code will be absolutely identical if you choose to deploy it on CPU, GPU, a neural processor, and FPGA. The ONNX runtime is going to do the work of parsing and partitioning the graph. By the way, it's also available in C. I didn't just show it. So additionally, we have a service in Azure called AutoML. AutoML allows you to give your data, then it proposes a model and provides you the application that you would be using. So if you had your code in a model in Python and your code in C# and you needed to do all the conversion, AutoML allows you or automatically does the conversion for you. There is no need for you to do any kind of recoding, and it definitely reduces the time for you to go from transitioning your models to ONNX and as well as deploying it in the ONNX runtime. And then finally, as it relates to building your own application, we have published a Docker image that you can pull from Docker Hub. This is a fully enclosed, all-inclusive container that you can run. It includes converters for the different frameworks, as well as it allows you to quickly get started with ONNX runtime and run some sample applications. So this could be a great way for you to start up your own environment and start running and coding your application to use ONNX. So I showed you a little bit of like all the different places that you can use ONNX runtime. So how many of you are now ready to see some demos and code? Okay, let's do it. About time, right? Okay, so what I'm going to show you is a workflow of taking a model, either from custom vision, Azure machine learning, or bringing your own model. I'm not going to cover that part. That is part of our, there are lots of sessions around experimentation and training. So what I'm going to start with is that you now have a model in ONNX. Once you have the model in ONNX, how do you go take it through the workflow to go deploy it in a service and then run an inferencing session? And we'll do that through Azure Notebooks. What's an AI demo without a Jupyter Notebook, right? Let's see if this switch would work. Okay, it does. So just blowing this up a little bit. So the same workflow that I showed you in my chart. So this is what the Jupyter Notebook will walk you through. We will first register a model. This is an example of a facial expression recognizer that we pulled from the ONNX Model Zoo. It's a ready-made pre-converted model, ONNX model, that we pull from the ONNX Model Zoo, and I bring it to my shell in Jupyter. Then I will set up my Azure Machine Learning workspace and register my model. This is the first step of bringing your model into your AML workspace. And then you can start using it and manipulating it. So this is the model registration step. I commented it out because I had already done it previously, so I did not want to redo it. In that case, I can just point to an existing model in my workspace. That's the code that we have. And by the way, all of this notebook will be published and be public, so you will have access to it and you'll be able to play with it. So this shows you the list of models. Just to validate it, I have now the set of models in my registry. I have the ONNX emotion model. That's the one that we are going to use. Once I have the model, I will write a scoring file that allows me to code up what would be the pre-processing step, what would be my inferencing step, and how do I load the model here. So this is the score.py file that I'm writing within my notebook. So as you can see, this is the step for loading the model in the init function, and then for running, this is my session run step with the input data. And then I have a couple of functions about pre-processing for this specific FER plus model. Then within Azure ML, I can create a container image for the specific target that I'd like to go deploy to. Container images are going to be endpoint specific. So here is where you would have to determine what your target compute environment would be. If you want to deploy it to a GPU-based AKS cluster, or you want to deploy it to an IoT endpoint based on ARM, that's the kind of the decision that you'll have to make now, because the image registry will include a set of base images that you will have to use to write your application on. So what I'm showing here are essentially two images that I create within the same Jupyter notebook. I'm creating a GPU image, as well as in the next cell, I'm creating a CPU image. In the GPU image, I am pointing to a base image that we have pre-built. This is an ONNX runtime base image for TensorRT. We have worked with our colleagues at NVIDIA, and we have published this in MCR. You can then use this base image to add your model and your scoring file to create the container image that you would deploy for your application. Once you do that, and similarly, we are doing a similar one for CPU. And for CPU, this is a generic CPU-based image for Ubuntu x64. Once the images are built, and I'm not running through this only because it takes time, and I don't want to have to wait for this process to work, we would then deploy it into a cloud AKS service. To deploy the cloud AKS service, first, again, within my AML workspace, I can use an existing AKS cluster that exists and build it and build that deployment target that I would use. So here I've called it an AKS CPU as well as one that I have called CPU. Obviously, I should have thought about the naming in my demo. But the point is that one is a GPU cluster, as the name suggests, and the other is a CPU cluster. So now that I have the two AKS clusters deployed, I push my workspace. I push the images that I built from my in my configuration to these respective clusters, and I now have a servicing endpoint that I can use to send some test images to. So here is the pre-processing step for any image that I may send. And I am going to now show you a quick set of, I've preloaded a couple of images here in my code, and I'm going to run an inferencing session. I'll run the inferencing on the CPU endpoint as well as GPU endpoint. I'm doing that only to show you that with the same code, all I needed to do was deploy this container to a CPU container instance or a GPU-based container instance, and I get different performance. And essentially, allowing you to minimize the specific hardware-specific code or target-specific code that you would have had to write. So here in this cell, and I'm going to zoom out so that you understand, I preloaded a couple of images in my workspace, and I'm going to run this cell to show you that what the pre-processing step detected. Okay, that's a face. Now we have cropped the face, and I'm going to run this in my GPU as well as in my CPU in this next cell. So when I run that, it send the image to that endpoint, and I see that no surprises there. That emotion was a surprise, and you get the inferencing latency across GPU and CPUs. Here's a quick graphical representation of what the performance was. What I'm going to do here is go back, change that code, and use this test image that I pulled from the web. So this was a test image. Very different, right? And then again, send it to my CPU and GPU endpoints to see what the expression is. Okay, it's anger, and therefore you see the inferencing latency differences. So switching back, that was a quick demo within one Jupyter notebook to show you that using very similar or identical code, you can now point your application towards a specific hardware platform and choose based on ONNX Runtime and using the flexibility of ONNX Runtime, CPUs versus GPUs, x86 versus ARM, cloud versus edge. Next, okay, here's a clicker. Next, I'd like to quickly show a demo about deploying ONNX Runtime and ONNX models on edge device. What I have here is the Intel Up Squared. And this demo is also available in the Intel booth in the expo floor. If you have not gone there, please check it out. What this is showing is a representation of a factory worker scenario. If the model was pre-trained to detect a safety scenario, specifically in a fab, and I think it was we use the training data from an Intel fab. The model is deployed on the Up Square as an ONNX model with the ONNX Runtime to run a pre-recorded video stream and show you the inferencing results. Quickly show the video here, and then I want to show you the code. Let's see if, okay, so I had set up the environment. What I'm going to do is I'm going to run this Python script, the cleanroom demo cpu.py, but I will show you the code in more detail so that you understand what we were doing here. What this is doing is loading the model, the ONNX model, onto the ONNX Runtime, and then using the pre-recorded video feed, showing the inferencing result and the post-processing of the bounding boxes here. This is basically the quick and dirty video of how it will manifest itself on the edge. But the more important thing I wanted to show you was the code. So switching back to my machine here, this is the same cleanroom demo.cpu file that I was running, and here blowing it up a little bit. So there are a couple of steps I wanted to highlight. So here we are loading the ONNX model using the same inference session command that we talked about. Before that, we did import the ONNX Runtime Python wheel that we have built. This is the pre-recorded video file that I talked about. And then within the loop, we are resizing the frame to match the shape that the model was expecting, and then initiating the session command here to run an inference session on that ONNX Runtime. So what I wanted to again show is that while this is running on an x86 Atom class processor on the edge, the code that we used is identical, but it's using different hardware accelerators to run the inferencing session and help optimize the application. With that, I'd like to ask Rajiv and Nathan to come back to stage so that we can get some questions answered. While we do that, actually, you guys should please come forward. While we do that, I want to also summarize what we did. We talked about ONNX and how ONNX becomes the common format to represent neural network models or machine learning models, and that we can then use the ONNX runtime to go deploy in the cloud and the edge. And with Azure Machine Learning, you can use our services to build your application and deploy in a variety of targets. So in terms of learning objectives, we talked about why we want to use ONNX, where you can use this, as well as building applications using Azure ML. Sorry, this is animated and I didn't realize it. Okay, so hope this was a useful session for you, and we are here to answer your questions.
Thank you.
Hey, thanks. Great session. Regarding the clean room training data you have, are you going to open source that? Because I think that could be useful for other people, as like for workplace safety scenarios, to release it as a pre-trained model.
We will not specifically that, but we will continue to expand the ONNX model zoo, which will include the data that was used. With regards to this specific scenario and this specific data, that's TBD. But we are going to continuously expand the ONNX model zoo with targeted scenarios.
Right. Is it a tiny YOLO, or what kind of?
That was a tiny yellow V2, yes.
Okay,
yeah.
Cool. Thanks.
Hi, great session and very informative, so thank you. You were showing that when you're running models on the face recognitions and expressions into different GPU and CPU, and it turned out GPU is a lot faster. Do you have a general guidelines on, just a general guideline on what machine learning or what model is good with running in a different CPU, whether it's ARM CPU base or GPU or CPU or things like that?
So generally, GPUs are better when you have batch inferencing, and you will not see so much benefits if it's a single inference on CPU versus GPU. CPU versus ARM, that's really a question of your deployment environment and what you're trying to do. The optimizations that we have for the math operations in CPU versus x64 versus ARM are using different libraries. But we see similar performances on both. There isn't an apples to apples comparison because you have such a wide variance in the type of ARM and x64 CPUs.
Okay, cool. Thank you.
Yeah, I want to add something. So usually we see more speed ups for those image models than comparing to those IM models like natural language. We have seen GPU can provide more speed ups over there, and especially if you have some model very cheap, then probably you don't expect GPU can provide more accelerations there because when you bring them data from CPU to GPU, there will be some cost, right? So only if the benefit is bigger than the cost, then you can see the speed ups.
So 2 questions. One is, can we right now using ONNX, take an existing Scikit-learn, pipeline and run it on a C# application using ML.NET? Did I catch that right?
Yes, for Scikit-learn is targeting for the classic machine learning, right?
Yeah.
So basically, we have Scikit-learn to the ONNX converter. So once you convert the Scikit-learn models to ONNX, then you can use ONNX runtime. And ONNX runtime is available in multiple languages. For example, we have C API, and we have C# API, and we have Python API. And ONNX runtime is also integrated to ML.NET. Right? It's available for the .NET communities. So you can use C# to run the Scikit-learn models there.
And is there a way to go from ONNX back to go the other way? Or that doesn't make sense.
Yeah, so we haven't seen that the going back yet, because like for those frameworks, well-known frameworks, so what we want to do is like once you convert a model to ONNX, you can choose whatever framework. For example, if you convert like say Pytorch model to ONNX, and you still can use Pytorch load ONNX model for serving, right? So same thing for like MXNet, CoreML, right? Those well-known frameworks not just convert to ONNX, they also can recognize, can load ONNX model for serving. So you don't have to convert back. You can just use it directly.
I'd just like to add that in addition, we support within Azure Machine Learning for you to upload inferencing telemetry back into your retraining or your experiment, so you can rebuild your model and then go through the conversion to deployment pipeline through that.
So the actual ONNX files, then you don't need to version those independently?
So you would, as you said, right, it's going to be one way. So you would retrain back on your original framework and then convert that trained model or the new trained model to ONNX and then
Got it.
so
Thank
on.
you.
I saw that you have the window ML support. Do you have integration with Excel natively now, or is that going to be on the pipeline?
I'm sorry, can you repeat your question?
Yes. Will you have native support within Excel to deploy models for scoring within Excel?
Within Excel?
Correct. So one of the other sessions, they had a function with the Azure ML to deploy the model and then score it within Excel. But that requires you to hit a REST API. Would you be able to do that with Window ML and natively integrate that with Excel?
You repeated the question.
So again, I'll repeat the question. So I think you're asking, would we be able to integrate ONNX natively within Excel? That's your question, right?
Right.
Do you want to take that?
Yes, we actually have been actively integrating ONNX to the all the Office products. But I guess there's some active work going on, but that's not for specific for Excel. It's not public yet. So you will see that like once it's available. Thank you.
Thank you.
Just two questions. What kind of file format is on ONNX, and how hard for us if we are going to create our own algorithms and convert it to ONNX?
You can use Python to parse that, your file format and convert it to ONNX.
Mm-hmm.
So basically, the converters allow you to, use a file parser to generate the ONNX graph from your graph. But it'll be a question of what is your input format going to be in. You will use one of the existing frameworks, assuming, correct?
Yeah, I'm just wondering if we just have a very basic algorithm, 1 + 1 = 2 or something, and we would like to convert that into ONNX, because yeah, we kind of use some custom algorithms in our work, so.
Yeah, so I want to take that. So if you look at the ONNX file format, ONNX is IR. So basically, it's an intermediate representation, right, in the middle. So if you look at the spec and eventually the file format is basically protobuf. Then we have defined the schemas, about the model, the graph, the nodes, right? Then you can just, simply use Python or whatever tool to manipulate that protobuf file. Then you can get your own ONNX models.
All right, thank you.
Yeah, thank you.
Okay, thanks. Oh, more question.
What is the approach to signing the ONNX models for distribution to make sure that they haven't been tampered with?
You repeat.
So, the question is, what is the approach to signing ONNX models for distribution so that we know that they have not been tampered with, right? I think that's a good question. I think we will take that back as feedback, as something that you would require. But from generally speaking, The model itself, the signing or securing that file is not going to be specific to ONNX itself. Because it's going to be an asset within your application. So we would say that you would use the same, any existing infrastructure for applications or for securing files as would be the same. But if there is any specific something, we would definitely take that up. Good input. Okay, thank you very much. Thanks for spending your time with our session.
Thank you all.